Ahora veo veo esto.
Sí, ahora empezó. Ha empezado. Es que me comentas como con 15 segundos de retraso.
Vale, pero es lo que es.
Sí, sí.
Vale, ahora te veo a ti. Pero no estás haciendo lo que estás haciendo ahora.
Ya.
Pero aquí no hay ninguna acreditación en Place.
No.
La secretaria de Álvaro la apartamos en un momento, la apartamos porque acabamos de haberla apartado todas y ahora ya empezamos.
Aquí hay una, pero no.
Vale, ahora vamos a cerrar la cutre. Voy a girar mi... Giramos el ordenador, así apunta al speaker, ¿ok? Hacemos así a la cutre.
Vale. ¿Ya quito esto? ¿Te quito el mío?
No, déjalo, please, por si acaso. Claro, ahora, como no reconoce el sonido, se vuelve loco, ¿eh?
Ahora ya está mirando a la pantalla y al speaker.
Vale, guay. ¿Y de ahí se escucha?
A ver. Sí, se me escucha a mí. A mí. Y a ti.
A ver, voy a la seta, hablando.
A la seta no se oye, está tu micrófono por aquí.
Vale.
Aquí este, a ver, micrófono. Vale, prueba otra vez en la seta.
Vale. Vale. No. A ver. Voy a hacer esto, ¿no? Micrófono, no sé este. Igual.
Pero sí que debería ser porque se suena, o sea, suena lo de fondo. Porque si nos acercamos aquí, ¿suena más? No, suena lo de fondo.
Es que lo que a ver, el Realtek suele ser el que viene incrustado en el...
Altavoces, claro, ¿esto qué es? ¿El altavoz nada, no?
No, el altavoz no.
Micrófono, es eso, ¿no?
Es que solo detecta el Realtek y el Realtek es normalmente suele ser el...
A ver, espera, es que está apagado. A ver ahora.
Hola.
Title, okay.
Claro, para probar la cosa.
The first one will be the food classification is the first one. Yeah. Thank you.
It's a electronic one, so you have a new slide, you have to point to the middle of the slide, so that's the point, and then to take the reference of the screen. This is an electronic one. Okay. So when you are lost, you change the slide and you point to the middle of the slide, and with the point to look the reference. Okay. You will manage it. Okay, so good morning, everyone. I think we should start already. We are already 5 minutes late. So welcome to the School on High Performance Multi-Layer Molecular Dynamics Approaches, which is funded by the Red Española de Supercomputación. We are very happy with the, let's say, the amount of people who has registered. We are around 60 on-site participants and around 80 online participants officially registered, because some people probably will join without unofficial registration in our YouTube channel. Okay, so I will only talk for 2 minutes because we are already late. Only a couple of practical things that you need to know. So as you know, we have a very crazy timetable. So I ask the speakers, now Felix is the only speaker here, so I ask them to be more or less on time, please, because otherwise we're going to finish at 10 in the night today. Okay, so let's say the timetable is always the same. Every day we have 2 hours theory lecture, coffee break, another 2 hours of theory with other lecturer, then lunch for 1.5 hours. And then in the afternoon we have the computer exercises, 2 computer exercises of 2 hours each, with a coffee break in the middle. So that's the timetable more or less for all the days. Okay, tomorrow, remember, we start tomorrow and the other days at 9, so half hour earlier than today. Okay. Okay, so we are here. So this is the entrance of the faculty, the main entrance. So probably most of you enter the faculty to this point, and you turn right, and then we are here in the module number 8. So we are going to have the theory lectures, all of them here in this room. Then in the afternoon, we are going to have the computer exercises here in the module number 6. I think this is in the first floor, I guess, right? So we have to go downstairs 1 floor or upstairs 1 floor. Okay. Okay, so, and then the coffee break, but the first time we can go together because it's a bit difficult to arrive there. The coffee break is on the other side of the faculty here in the module 13, which indeed is our department, the Department of Chemistry, in the fifth floor, no floor, in the fifth floor. Okay. So, but anyway, today we can go together and then for the next time. Okay. So coffee break is included. Lunches, as you know, are not included, so you have to pay by yourself your lunch. Here we have a very nice cafeteria. No, it's not nice. We have a cafeteria, but we also have another places in the campus, so you can ask our local students, and they will tell you where to go. Okay. Okay, so I would like to finish saying thank you to all our lecturers. I think we have great researchers from around the world. They are really experts in their field. So thank you very much. And also most of them are very good friends. So we are happy to share these 5 days with friends. So, okay, that's it. Now I would like to introduce Ines, who is also the organizer of this event, and she will introduce our speakers. Okay, so welcome.
Okay, so good morning to everyone, and thank you for coming here and joining us for this school. Please, I'm just going to steal Felix a couple of minutes, but I would like to say a few words on his background. So Felix got finished his bachelor studies in 2008. Then he got his PhD in 2012 under the supervision of Hans Lischka. Basically, the topic was DNA, the physics of DNA. Then from 2013 to 2015, he did his first postdoc, hosted by Professor Albert Joy at the Ruprecht-Karls University. So I apologize for my German, it's a long time since I don't practice it. Then from 2015 to 2017, he did his second postdoc, hosted by Professor Leticia González at the University of Vienna. And since 2018, he's a lecturer in chemistry at the Loughborough University in UK. And yes, so his main interests are basically for excited DNA, molecular electronics, transition metal complex, and also excited state aromaticity. So he's an excellent researcher. He has excellent metrics. So he has an H index of 41, almost 7,500 citations. And he's an even more better lecturer. So, well, he's going to teach us about his development on Theodore, I guess, with functional analysis package. So please, Felix, go ahead.
Yeah, thank you, Ines, for the introduction, and thanks everyone for coming. So usually I only talk in front of undergraduates, they always look really tired and bored, and no one's ever smiling. So it's kind of, nice to talk about the people that actually care about what I'm trying to teach them. So nice to see you here. So yes, as I want to talk about, excited states, I guess, I don't have to convince you that excited states are great, otherwise you wouldn't be here. So when we think about excited states, it's when a photon when a photon of UV-Vis radiation interacts with a molecule. We need them for technologies, for OLEDs and solar cells, and we need them for biology. And when you think about photosynthesis and photo damage, and as a scientific tool where photocatalysts, sensors, and so on. So, for example, when we talk about excited states, we have the bright states. Those are activated when a molecule interacts with a photon of light. Those are involved in absorption and emission. Of course, we have also lots of dark states that will be involved in photoreactivity and deactivation. So now the idea is that we have all these applications. Let's see, find this so confusing. Yeah, we have all these applications. And and then all these applications have different underlying physics. And then the question is, how do we talk about these things?
1 minute because we are not sharing the screen. Sorry.
Okay, so then the question, what I tried to kind of convince you here that excited states are really important. They come in a wide, kind of in so many different varieties, and now we should think about how to talk about them. And I just want to give you a quick overview and then talk about some specific ways that we use to talk about excited states. So, kind of how do we, what is the textbook picture? The textbook pictures, we have our occupied orbitals, and then an excited state means we take an electron from an occupied orbital and place it in an unoccupied orbital. And then, depending on the different orbitals involved, we have different excited states. This is, it's a good starting point. It's kind of the way that we can begin talking about excited states, but it's clearly not the whole story. So why is this orbital picture not the whole story? The reason is that underlying all of this, we have many electron wave functions. I mean, that we use these extremely complicated quantum chemistry methods. And why do we have to use these extremely complicated quantum chemistry methods with lots and lots of latches in them? The reason is because electronic wave functions are very complicated many electron objects, and we can't just look at molecular orbital transitions. So kind of in this picture, we capture the full physics, but I mean, we can't deal with this really complicated object in many electron wave functions. And then the question is, where, what is there between those two areas where we can actually learn something about excited states? So, so I want kind of in this talk, I want to talk about physics of excited states. How do we talk about physics? What kind of language do we use to talk about physics of excited states within and beyond the MO picture? So this is what I would call excited state classification. And then the next talk will be more about practical tools that we can use to analyze excited states, just to make things quicker, but also to kind of uncover the physics we talk about in the first step. So how do we classify excited states? And again, kind of the thing that probably is the starting point for most of us is that we say, okay, we have pi star states, we have n-pi star states, and so on. So we're talking about the molecular orbits involved. But then if you look through the literature, then other people, then of course you can also talk about what molecules and fragments are involved, local excitations, charge transfer states. And then you could talk about spatial and spin symmetry. You could have one AG state, you could have 3B2U state, and so on. We could talk about mathematical wave function properties, like is the state single and double excited? Is it multi-configuration or something that only makes sense once you can look deeper into the wave functions? And then there's also some other alternatives that end up being used that come up, in the different papers, and often it's not even so clear what they mean. We can use the valence bond picture, we can use the Plasser nomenclature, and we can talk about excited state aromaticity is one thing that I kind of found exciting recently. So, and just to give you an idea, kind of, we went through a literature and searched for all the ways that people use to talk about excited states. And when we start out here, usually we go to MO theory, look at valence states, and then with pi star states, n-pi star states, and so on. So that's, usually how we start talking about excited states. But then, of course, staying with MO theory, we don't only have valence states, we have Rydberg states or covalent states. And then, as a more special case, we have, metal stable resonances. Then, something that most of us are familiar with is probably if we talk about extended systems, we could have charge transfer states and locally excited states. For transition metal complexes, there's some kind of more detailed classifications in metal sense, metal to ligand charge transfer and so on. Then we could talk to excitons, plasmons, eximers, down here for extended system. Then, of course, spatial symmetry and spin symmetry. I mean, that's something that I guess also comes in the basic textbooks. Then I really like these three boxes, and that's something that people don't talk about so much. So that's kind of, when we have pi star states, different ways to classify them. And we'll talk about valence bond theory, where we have ionic and covalent states. With the Platt nomenclature, LA and LB states, and I'm sure if you read papers about excited states, you see these things coming up. And then we can talk about excited state aromaticity. And then the one box I haven't talked about is more fundamental properties. How many electrons are excited, singly excited, doubly excited, can have multi-configuration, single configuration, correlation, and orbital relaxation. So I mean, the main take-home message here is that these excited states are really complicated, and you shouldn't just kind of draw a picture of an orbital and say that's all there is. And if something comes up, if something is a bit strange in the computation, if some weird physical phenomenon happens, then just remember, okay, that there's so much more behind it than just kind of orbital pictures. So that's the message for this one. So. Okay, now we'll go through it, and I'll start with molecular orbital theory. So molecular orbital theory is kind of the thing that all of us are familiar with, and I just want to kind of start slow. We divide the MO space into core MOs down here, valence molecular orbitals. The valence orbital can be bonding, non-bonding, or anti-bonding, and then somewhere up there we have kind of the diffuse molecular orbitals that represent the continuum, or that are connected to the continuum of a free electron. And then we just kind of classify the state according to the MOs involved. So I'm sure that's not anything new to most of you, but it's kind of starting point that I want to use here. So we take an electron out of a bonding or a non-bonding orbital, and we put the electron into an anti-bonding orbital. So, Kuiper star states, those are usually the bright states, tend to be Kuiper star character. But again, not all Kuiper star states are bright, and we'll talk about different classification schemes for Kuiper star states later. That's the other, very big thing that we always have of N-pi star states. Those are usually dark, but they can play a very important role in during the photodynamic processes. That's why it's important to remember that they're there. Then, if we mix some other orbitals, we could go into an antibonding sigma orbital, pi sigma star, sigma sigma star. And, for pi star orbitals, you still have the sigma system that holds the molecules together. So that's why pi star states, are still kind of stable things. If you excite into a sigma orbital, then you don't have anything that holds the molecule together, and that's why pi sigma star states or sigma sigma star states are often dissociated. So when you think about it, we put one electron here. At some point, we just have a free hydrogen atom here. So when a molecule dissociates, then we usually talk about something sigma star in there. So then, that were the valence states. Most of the time we're dealing with the valence states, but sometimes we can't ignore Rydberg states. On the one hand, they might just kind of appear in the computations. On the other hand, of course, sometimes spectroscopists are specifically interested in Rydberg states. The Rydberg states means that we're excited to diffuse orbitals. So when we draw the orbital is really big and diffuse. And the physics here is that we think about the molecular orbital, a molecular ion circled by an electron. So in a sense, the molecule just becomes a point charge, and then we have a diffuse electron circling around. And then we can kind of think of Rydberg states as just, like effective hydrogen atoms. And that's where the name Rydberg comes from. So you have the Rydberg series of the hydrogen atoms, the Rydberg constant of the hydrogen atom, and this is just, a Rydberg state is just a big hydrogen atom. So then when you try, you can find, you have an S orbital, or you could have P Rydberg orbitals, the PX, PZ, and PY orbitals. If you play around with it long enough, and then if you keep going, you can find D orbitals and so on. Then maybe just one point here about Rydberg states in practice. So I mean, if you pay attention to it, then you can get these really nice pictures. But let's say in practice, when you see Rydberg states, and usually a Rydberg state in practice, you recognize the Rydberg states by the fact that you don't see anything. So you know, this is a Rydberg state, you know, for the adenine molecule, and I just use some kind of a default cutoff of 0.04 atomic units. I can't ever remember what is actually the unit of these things. But anyway, if you use the cutoff of 0.04, you don't see anything except if you look very close, a little blob here. Then you reduce the cutoff and you see some kind of little blobs here, and then you can kind of imagine, okay, the orbital actually happens outside of the molecule, and then if you make the cutoff lower, then you see, okay, you have this big blob around the molecule. So be careful when you kind of see that you don't see anything, then maybe you have to reduce the cutoff. And then, you know, if you want these really nice pictures, then you have to render it at very high resolution, you grid at very high resolution, and then, you know, and then, for example, this is made in BMD, where you directly read in the grid rather than the error coefficient. Okay. So, yeah, I didn't prepare a lot about covalences, but of course, just kind of to make this complete, of course, we could also excite from a low-lying core electron into the valence space. Then that's kind of what people are interested when they're doing X-ray spectroscopies. Like anything that starts with X, like the Zanes, or I don't know, X stars or whatever. Then you always have like these core valence states involved, and you know, the energies are usually high, we're talking hundreds of electron volts, kilo electron volts, and so on. So, okay, so we've been talking about kind of the ammo picture, but I think something that's, in my opinion, underappreciated in the field is kind of other ways that we can use to talk about excited states, especially Plasser states. So, we know that polycyclic molecules have a large number of Plasser states. So, you know, any kind of nuclear-based heteromatic molecule, even things like naphthalene, you have like all these different Plasser states. And it's just kind of boring just to say it's a Plasser state. And often helps us some further classification. And the reason is, you know, if you have different ways to talk about them, then you can predict the energies, brightness, reactivities, and so on. So it's not just kind of that you have to put labels there, but kind of that these labels then allow you to know things about these different states. So, and yeah, one thing that's kind of, you know, that comes from the 70s or even earlier than that, but people stopped looking at that as the ionic theories. We'll look about it in terms of resonance structures, ionic and covalent resonance structures. Then we have this Platt nomenclature and this Terrace's plus minus nomenclature that sometimes, I think it's just read with one R. And I'll talk about that. And something else that kind of recently kind of fascinates me is excited state aromaticity as a way to think about excited states. So, valence bond theory means we analyze a state in terms of covalent and ionic resonance structures. I'll show you kind of what this means in chemical terms in 2 slides if you don't know what I mean with this. And then we can kind of, you know, and if we do that, for example, then we have some really nice way to think about difference between singlet and triplet states. So kind of, why is a singlet higher in energy than a triplet? And also, about multi-configurational excited states. So if you look at a molecule like naphthalene, for example, you have the HOMO -1 to LUMO transition, the HOMO to LUMO +1 transition, and then you can either have a minus linear combination or a plus linear combination between those. So often, you have these quasi-general configurations with different signs, and then this valence bond language offers you a way of separating those different states. So, okay, and I think, you know, even the ethene molecule illustrates most of the things, or I mean, it illustrates a lot of things that are important for HOMO-LUMO transitions. So, you know, so we look at ethene, the HOMO and the LUMO, all that matter, and then we can construct a singlet and a triplet states. And now we know that the triplet is HOMO-LUMO minus LUMO-HOMO, and the singlet is HOMO-LUMO plus LUMO-HOMO. So now we just, you know, alpha HOMO beta LUMO minus alpha LUMO beta HOMO, and this is plus. So of course, I mean, with these signs, you always have to be careful. But if I write it down like this, then the triplet is going to be minus, and the singlet is going to be plus. And now one of the questions is, you know, what is the difference between a triplet and a singlet state? So why are the energies different? How can we think about the different wave functions? And here, this valence bond viewpoint offers us a very nice way of looking at that. Because the idea is, you know, we expand this in localized orbitals. So here we have the delocalized canonical orbitals, here the localized orbitals. Now we can think about the HOMO, that's just a constructive linear combination of those, so it's A plus B. And the LUMO is the destructive linear combination of these, that's A minus B. And then, you know, in the coffee break, you can try doing that. Just insert this expression and this expression into the triplet and the singlet expression. And then when you try doing that, you know, then you'll find out that the triplet is going to be BA minus AB. So that these are biradical configurations where kind of one electron is in A and the other one electron is in B. And then the singlet is going to be AA minus BB. So for the singlet, you have ionic configurations where either both electrons are in A or both electrons are in B. So yeah, so that's the difference between singlet and triplet. Singlet is ionic, triplet is biradical, and that kind of that always counts for, you know, for HOMO-LUMO transition alternating hydrocarbons. So if I would say if the HOMO and the LUMO are basically on the same path, on the same atoms, just a different nodal structure, then you can always express it in this way, where the singlet is ionic and the triplet is biradical. So, and this gives you a nice interpretation for singlet triplet gaps. So on the one hand, you know, you can compute the singlet triplet gap on the left side. If you compute the singlet triplet gap on the left side, then you know you kind of apply the Slater-Condon rules. What is the coupling element between this one and this one? So basically, to go from here to here, you need a double excitation, because you go from alpha HOMO to beta HOMO and from beta LUMO to alpha LUMO. So then kind of the coupling element between those two is the HOMO-LUMO exchange integral. And then you find out, you know, in the molecular orbital picture, the singlet triplet gap is twice the HOMO-LUMO exchange integral. But then you can also look at the singlet triplet gap on that side, and on that side, the singlet triplet gap is the energy required to move the electron from here to here. So it's the difference between the Coulomb repulsion on two different sides and the on-site Coulomb repulsion. And again, you know, if you want to have even more time in the coffee break, I mean, after this, you know, you can easily derive it if you just use Slater-Condon rules and then kind of transform the integrals according to kind of these rules. So again, kind of FDN is the molecule that shows you the basic step. I just wanted to use a slightly bigger molecule. I hope you can see this. So you know, it works with most of these molecules, but kind of the idea is that alternating hydrocarbons, so this you don't have 500 rings, so that, you know, that you can think about kind of two, you can put a star on half the atoms, and then all the atoms with stars are bonded to atoms without stars. But I mean, but that's a lot of molecules. So then, for example, here I'm using this thing called paraquinone methane, just because it's kind of an interesting molecule that shows you biradical and ionic resonance structures. So this is our molecule if we draw it completely bonded. But then we can have ionic biradical resonance structures. So we look at those two sides. We can put radicals on those two sides. And you know, for these specific molecules, if you put radicals here, then this ring becomes aromatic. So that's why these radicals are stabilized. But you know, the thing that I'm showing you here works for any molecule where you have kind of two distinct, where you can kind of have two distinct sites where you can put the radicals. So this molecule is going to have two biradical resonance structures and two ionic resonance structures. So this is exactly the same that we had before with ethylene. Here I'm just using a slightly bigger molecule just because it's kind of fun, you know? So it's the same with the biradical and ionic resonance structures here. We have it here, and the important point is that kind of these structures we can identify with ionic and with biradical and ionic resonance structures as we would draw them in the valence bond picture, the Lewis structures. Then in the first step, we have to perform symmetry and spin adapted linear combinations. So if we combine those two resonance structures, then we get Q states that are split by twice the exchange integral between those two. And then it turns out that kind of the lower state is a triplet BU state, the higher state is a single AG state. If we combine those two structures, then they're also split by twice the exchange integral. And then you get a single BU state and a single AG state. So this is just going to have to get the symmetry adapted linear combinations. And then when we turn on the full Hamiltonian, then we see that the AG states mix. So the one AG states mix. The one AG states mix to form this one bonding and the anti-bonding. So the closed shell, bonding closed shell, anti-bonding doubly excited state. And kind of here, I don't know if, I think that's most of kind of the elementary quantum chemistry textbooks. That kind of, you know, a closed shell in the MO picture is actually a 50-50 linear combination between biradical and ionic resonance structures. So I think that it's something like Jensen's computational chemistry is how Austin. I think that's something you'd read there. And I mean, you can say this about, you know, the H2 molecule as well, but you know, it holds for this bigger things as well. So when we think about closed shell molecules, then they're even mixture between ionic and biradical resonance structures. Okay, then the next point along the story is now the triplet BU state and the single BU state, they can't mix because of different spin multiplicities and different symmetries in the other states. So the triplet BU state always stays biradical, and that's wrong actually. The single BU state, no, this is correct. And then the single BU state always stays Switter ionic. So here in the localized picture here in the MO picture. So that's kind of the other explanation why we think about triplet states. So triplet homologous states is biradical and singlet homologous states is Switter ionic. And you know, and I think this also tells you some other nice things. For example, let's say we could also kind of live between here, where, you know, we don't have the full closed shell, but we have some biradical character. And you can think about it, you know, if the molecule gets some emerging biradical character, you can also think about it in the sense that, you know, that these ionic configurations are just become separated from the biradical configuration. So if you have a biradical because the bond breaks, or just, you know, just because the energetics change, then it's kind of like, you know, you're moving back along this line. Yeah, and then kind of another thing we recently talked about is, you know, the question, you know, that in polyenes, the double excited AG state tends to be below the BU state. But the point here is, you know, in this two orbital model, the AG state is always above the BU state. So in the two orbital model, you can never have kind of this idea that the double excited state is below the single excited state. But you know, it only happens when other orbitals mix together. Okay, so but the main thing I want to say is that kind of going back to this valence bond description just, I think, provides a lot of information in a way that we don't get from the MO picture. All right, then let's see what else do we have. And I don't want to go into that much detail here, but if we, you know, for homolume transitions, kind of this picture works that I showed you here. If we have states that are not homological transitions, it's a bit more difficult because then we have different quasi-degenerate configurations that mix. And then one often uses Paris's plus minus nomenclature. Actually, Paris is with one R, but then there's also par with two R's. And this Paris a par potent method. So then we sometimes say plus minus to say how the quasi-degenerate configurations are combined. So when you see then something like this plus minus, and this comes from this Paris nomenclature, and then we also have this plus nomenclature with LA and B states. And I'll get back to that for the practical example in the second part. So I don't want to, otherwise it might be a bit too dry to just talk through the theory now. So, but I think another way that I like to talk about excited state is the idea of excited state aromaticity. And the way that I think it's good to think about is, we think about a 2D rigid rotor. So basically the ground state of the 2D rigid rotor is like an s orbital, nothing moves. Then the next state is p orbitals and d orbitals. So the difference between the 2D rigid rotor and the hydrogen atom is that you only have the orbitals that lie in the xy plane. So you have one s orbital, but then you have two p orbitals, px and py, and you have two d orbitals, dx squared and dxy. And now we can think about a molecule like benzene or any kind of ring is a bit like a rigid rotor from the point of view of the electrons. And then when we look at the orbitals and we see, okay, the first orbital really looks like an s orbital, no nodal plane. Then we have two orbitals with one nodal plane, and we have two orbitals with two nodal planes. So it counts for benzene, but for example, for molecules like butadiene, it counts as well. For every molecule, with rings, we get kind of this picture from the 2D rigid rotor with the important thing. First orbital is non-degenerate, all other orbitals are doubly degenerate. So, and then how do we get a filled shell? We get a filled shell if we have an odd number of electron pairs. So we have 4n plus 2 electron pairs, and then, if we have 4n electrons, then we might either get a half-filled shell or we get some kind of symmetry breaking, as is indicated here, where we have a low homoluminal gap. And of course, that's that's kind of the way of thinking about Hückel's rule. If you within this rigid rotor, usually you would derive Hückel's rule with Hückel theory or Hückel matrices, but I think kind of this 2D rigid rotor might be even a bit more fundamental way of looking at aromaticity and kind of why you always want an odd number of electrons. Because it's an odd number because you also have one orbital that's non-degenerate at the bottom. There's no angular momentum. Now we don't know much about ground state aromaticity. This school is mostly about excited states, and then the question is how what changes in the excited states, and now it turns out that for the triplet, the aromaticity rules are reversed, and that's what we call bad aromaticity. So when you think about cyclobutadiene, in the S0 state, it was very unhappy because it is large homoluminal gap, but now in the triplet state, it has this kind of closed shell feeling because you have one electron per orbit. And then for benzene, it's a bit different because when you promote the electron here, then it would be, but let's say if you promote the electron here, then it kind of would be this open shell, but there's two electrons to move around. What it actually does is it does a Young-Keller distortion, and you can interpret this as a Young-Keller distortion, but this degeneracy between those two orbitals is lifted. But again, you can see kind of for the same reason that ground state benzene is really stable, becomes that the excited state benzene is really unhappy. Just, because this one has this large homoluminal gap, and large homoluminal gap means that kind of the excited state is going to be unhappy. So, and that counts for triplets originally, that's bad aromaticity, but, it's the same rules also apply for single excited states. Because, ultimately, aromaticity is a statement about orbital energies, and then, the singles experience the same kind of orbital energies. So we can, use this language for singlet and triplet states. And and if you read the literature, then excited state aromaticity and anti-aromaticity can be used to understand, excitation energies and reactivity. For example, benzene is kind of paradigmatic case. You can understand benzene photochemistry in the sense that it wants to get rid of its excited state aromaticity. So in this very symmetric state, benzene would be unhappy, but if it undergoes distortion, if it folds or bends, then it gets rid of its anti-aromaticity. So whenever you have an aromatic molecule and then an excited state, you see ring puckering, it destroys the conjugation, then it's one way of interpreting this is relief of excited state anti-aromaticity. It just wants to get rid of all this conjugation because the conjugation makes it anti-aromatic. So that's why I think it's one nice language to talk about excited states. So just kind of a bit of an idea, is kind of the assignment of aromaticity and anti-aromaticity. So there are some specific aromaticity descriptors, but these don't usually work for similar excited states. But I mean, the idea is, if you have excited state aromaticity, then the number of nodal planes between the donor and the acceptor orbital is the same. And if you have excited state anti-aromaticity, then the number of nodal planes increases between the donor and acceptor orbital. And now the point is kind of most aromatic or heteroaromatic molecules, have this case that the number of nodal planes increases. And so the idea is that it's one possible language, this language of excited state anti-aromaticity, that applies, to most aromatic or heteroaromatic molecules. And then you can kind of use this to explain, for example, why does ring puckering happen, why does the structure change so much, because it wants to relieve the excited state anti-aromaticity. Okay, so that's Piper star system. The last section about the classification is how we talk about extended systems and interacting chromophores. So I think that's again something that's in more common use than the stuff we just talked about. So the point is, if we have the system interacting chromophores, we can add some kind of new physics that we can think about, new phenomena that we can label. So of course, we can transfer an electron from one part of the system to the other part. That's what we call charge transfer state. We could have a delocalized correlated state, and that's what we call exciton. And then we have, some other things that don't want to talk about, like plasmons or exciflexes. So again, that's kind of a rich photophysics also in this case. Charge transfer state, kind of the simplest case of charge transfer state is just we have two chromophores. This is adenine and thymine. And then you see the donor orbital is on adenine, the acceptor orbital is on thymine. So this is a charge transfer state from adenine to thymine. And one thing that always gets thrown around in the concept of charge transfer states is, if the chromophores are fairly far apart, then we can view a charge transfer state as an independent ionization and electron attachment. So we need the ionization potential for here, the electron affinity for here, and then the separation between the two molecules. So this works for charge transfer states, and even for locally excited states, you can kind of still have this effective exciton binding picture where you look at kind of ionization, electron affinity, and then some kind of an effective exciton radius that binds the exciton together. But for charge transfer states, we can really just talk about the distance between the two molecules. And then kind of the option two is, of course, kind of intramolecular charge transfer where a molecule with donor and acceptor groups. And maybe the thing to say here is that actually, if you think about most common chromophores, I don't know, like something like indigo or something like some kind of pH indicator, they all have some kind of donor-acceptor group, some charge transfer character. And then if you think about anything like, let's say, organic materials, molecular materials, there's always some donor-acceptor group, some charge transfer involved. So just to realize that almost everything has some intramolecular charge transfer character that we use in technology. So then transition metal complexes kind of also go in this area where we can think about charge transfer states. And yeah, maybe first to think about why do we care about transition metal complexes. Of course, we use them as photosensitizers, where they, can transfer triplet excitation energy somewhere. Photocatalysts, where they might, transfer an electron. Emitters, dye-sensitized solar cells, and so on. Now, when you do computation on transition metal complexes, you see that there are loads and loads of quasi-degenerate orbitals, known as E and pi orbitals, that are kind of mixed in weird ways. And and then there's quasi-degenerate orbitals give rise to lots and lots of quasi-degenerate states, and at the end of the day, it's all a mess, and you don't really know what to do. So it's tedious if you do kind of a manual analysis, but it's also error-prone because at the end of the day, if the orbitals are delocalized everywhere, how do you know what kind of state it is? So then kind of the solution for transition metal complexes is that actually we like to talk about them in specific categories, where metal to ligand charge transfer, metal centered intraligand, and then all these other kinds of CT states. And then we can think about, what do we mean when we say metal to ligand charge transfer? It basically means that the excitation starts on the metal. So here I use the word hole, where the excitation starts, and the excitation ends on the ligands. So then kind of this block is metal to ligand charge transfer. And then metal centeredness will start on the metal and will end up on the metal. Intraligand will start on one ligand will end up on another ligand. So then basically, now then we kind of, if we kind of have this picture in mind, then we can devise an analysis. The way how to do this analysis is part of the second talk. We do it with the transition density matrix, and I'll show you the kind of equations later. But the point, that once we realize this, then we have an automatic classification of state character in this system. We'll just press a button and we'll see, okay, it's metal to ligand charge transfer state. And you can even get some mixing. So for example, we can say, okay, you press a button and say, okay, this is 25% ligand centered, 75% MRCT. So there's some references here. I think at this point this works with the spherical convenient geometry. So then kind of the other thing is that experts of exercises in extended systems. Then when you do computations, you have all these different configurations involved. So the dominant configuration makes just 50% of the excitation with all these other electron configurations, orbital transitions involved as well. And so kind of the one picture is kind of all these different orbitals involved, so we have some kind of a correlation. That's what actually looks like in the MO picture. But then we can kind of try to move to the electron hole picture. It's more like what comes from the physics community. So kind of what is a hole? The idea is, you have the closed shell of electrons, but then you kind of say, okay, instead of the closed shell, I have a vacuum. And then, if I take an electron out of the closed shell and leave a hole in the closed shell, and then I put this electron somewhere else. And that's why you can talk about excitation in terms of electron hole, where kind of you say, okay, the closed charge is kind of Fermi vacuum. But from the chemist point of view, the hole is just where the excitation comes from, the electron where it goes to. And then we can think about the electron hole pair as being described by a two-body wave function, where the hole, described as coordinate RH, the electron is described by the coordinate RE, And then, you know, rather than looking at the whole of the electron, rather than kind of looking at, you know, the orbitals, the HOMO and the LUMO, we can kind of transform this, and we look at the relative coordinate, the electron hole separation, in the center of mass coordinate. And then you can think about, you know, you can either have the whole neutral quasi-particle moving in space, the center of mass motion, and this we can think about as a particle in a box. And we can, you know, kind of, let's say, a neutral particle moving around, scattering around the molecule, and then we can have the relative motion between the electron and the hole, and then we can think about this like a hydrogen atom, which is just an effective dielectric constant mass. So as we already had Rydberg states are a bit like hydrogen atoms, and excitons are also a bit like hydrogen atoms. So it turns out, you know, that kind of these basic models describe lots and lots of physics. Yeah, so in the second talk, I'll show you a bit more how we can connect this to quantum chemistry. So again, the conclusion of this first talk are, you know, that we have rich underlying physics for excited states, and you know, and we shouldn't just kind of plot a few orbitals and then say, okay, we're done. Only use a few orbitals. But there's you know, different models that we can use. We can talk about molecular orbitals, where we talk about valence and Rydberg states, valence bond theory, where we talk about ionic and biradical states, and then for extended systems of charge transfer and excitons. So yeah, thank you. So this is my first talk. So, okay.
You want to make a break?
Yeah, I'm trying to do like a 5-minute break.
Yeah, sure.
Okay.
By the way, as this is not a conference, you can ask questions in the middle of the talks if you want. Okay, so you don't need to wait until the end. Okay, if you have questions now, you can ask them.
Do you have any questions now? I'm really not like that. I have
3 to 5 or something like that. I don't know if you will wake up.
Yeah, I mean, I know people that do, but it's nothing. That's what you work on.
I think you will wake up.
You work on your. Who do you work on? Who do you work on?
We have a coffee break.
Okay, let's go.
A short break.
I'm really not about it, but of course, I mean, you know, with this whole I haven't ever this is kind of the case where you can
How is my
yeah, good. Just post stuff to work for me. First post.
Yo soy de Canarias, estoy en Canadá.
No,
soy de productor.
So, you know, publication always going well. Funding,
Sí, aparte sí lo hice en Barcelona. Y la
how is Loughborough? Is it
Yo soy
Plasser, right? Is it la?
sí, de las raras que tú dices. Bueno, vale, no te metes.
Yeah, like la.
Sí, porque estaba en la Autónoma y ahora vivo en La Rioja.
I think it's a nice, it's kind of a small university, but it's still, it's not have a place, and I think, I like the community.
No, yo he hecho un máster de humanización.
I always hope to
Yo hice dos.
but I think, I think
Yes.
it's good not to have too much pressure.
Qué suerte. Vale, sí, perdón. A mí me gustaron online, en plan, yo fue la mejor época de mi vida.
That's kind of nice to be out in the green, our house, and run, walk.
Sí, es una puntada.
I would like also to move from Malaysia to a smaller city. That is my college.
How long have you been?
Actually, I've been
O sea, eran 6 meses, 6 meses en la oficina.
I guess the university is kind of on the northern edge of the country. No, it's really move further north.
Ah, Buena.
Oh, yeah.
Solo lo tengo.
Yeah. Yeah, maybe it's still. Yeah,
it's also working on this.
No me valía mucho la pena.
It's not like
La migración doble máster de 2 años. No.
Now she went and is working for the government.
Bueno, me preguntan como de el máster, ¿no? Dije,
probably how old is already 10 years he's already out to school and
Here is 8 years old and it was a big old programs also. Released 8 years ago. It's kind
no,
of
no comía canaria, en plan.
No, I'm not sure I understand. So just let me know when you want to do it. So start 10 minutes later, 5 minutes later. I guess it's 10
De medicina, de fuerzas estamos muy españoles el rollo, pero ¿qué haces?
That's the second talk. So maybe we can talk after the second.
Desarrollo campos de fuerza y decir.
I'm not sure if it's
Voy a inventar uno, ¿sabes? Está curioso, ¿verdad? No, pero está curioso. Claro, al final yo, por ejemplo, los Warfare y todas estas cosas lo cojo. Gracias. Exacto. Muy bien, chicos.
Pañales, bueno, no.
Larga tarde con la espalda doblada en el ordenador, leyendo su.
Bueno, hay que pasar por eso.
En teoría me lo ofreció hacer, pero no sé si lo haré. No lo sé, no sé si me encanté, pero está guay, lo que la facultad
I guess you have some more. I guess we can talk about it maybe a little bit later.
Igual con eso no sé funcionar en plan. Ahora que voy a la misma, las programar.
Please, let's continue with the second lecture. To close it up. Okay, thanks for coming back. So in the first lecture, we talked about, how do we classify excited states? How do we, what kind of language can we use for excited states? And now this is, the second is what to do about this in practice. We ran a quantum chemistry computation, and we want to go to a phenomenological discussion. So we want to identify those phenomena that I just talked to you about. So, then the different things we'll talk about kind of reduced density matrices as our main workhorse. I'll talk to you about kind of the mathematics behind that, then transition density and difference density matrix. And then we have a couple of case studies. Let's see how far we get and how much time Juan forgives me after we started 10 minutes late. So I'll see how far we get. Okay? So everything starts with the Schrödinger equation. So what we're doing is, of course, we want to apply the Hamiltonian operator to our wave function and get the same wave function again, multiplied by a number. We do this for different solutions, so we get all different exciter states. And now the point to realize for this lecture is, that these wave functions are very complicated objects. You have all the different electrons swirling around in arbitrary ways. So then the question is, how can we talk about this one electron function, and how can we describe changes between two different many electron functions? And here kind of the idea, what do we do is we want to have a systematic complexity reduction through reduced density matrices. The idea of a reduced density matrix is the following, that we have our wave function with lots and lots of coordinates. And what we do is we multiply the wave function with itself or with its complex conjugate, complex valued wave functions. Then we integrate out over all coordinates except for the first one. And then we also put in a label. So the x comes from the first wave function, the x prime comes from the second wave function. That's what we get. Then we get what we call the one electron reduced density matrix. And we started with two wave functions with n electrons, or here, okay, one wave function with n electrons, and we end up
with a function that just contains two effective coordinates, two effective electrons. And I don't know which way you're more familiar with. One of the other ways is to write this in second quantization, or the creation and annihilation operator. So annihilation means we annihilate orbital mu in this function, and we create orbital mu. So at the end of the day, we select all the Slater determinants that contain this orbital mu and replace it with orbital mu. And then we get the density matrix in matrix form. So the weird thing is that actually this thing is called density matrix, even though it's a two-body function. And then this is the matrix of the density matrix. So that's just how these things are called. And then you can connect the above equation, that kind of the density matrix in coordinate form, which is the sum over this density matrix elements multiplied by the basis functions. It's not so trivial why this identity holds, but it doesn't. So, okay. So why do we like to talk about density matrices? That's because we can use density matrices to compute expectation values of one electron operator. So in principle, what is an expectation value? We apply the operator to the many electron wave function, multiply it with the many electron wave function, and integrate over all the coordinates. So that's what we mean by expectation value. So we're talking about dipole moments, angular momentum, kinetic energy, or generally speaking, a physically observable quantity. And now it turns out that if we have a density matrix, then our operator expectation value becomes this very simple form, where rather than having an integral over all n electron variables, we just have a summation over basis functions, so double summation over basis functions, and then we have to just evaluate this little one electron integral. So we have to, and that's usually what we call the operator representation, the representation of the operator in our basis set that we choose. So that's kind of the practical reasons why we evaluate these density matrices whenever we do quantum chemistry. So so now there's two nice things about this. First, they're always available because we need them for expectation values. And second, they're a rigorous thing with a clear connection to physical observable quantities. So that's why I like to use those. So I think it's a good starting point for a wave function analysis. Then I guess the thing that most of us are, yeah?
Good question. So that gamma XX prime is the, let's say, the actual one particle reduced density matrix, right? But that DBD, is it the matrix representation of that operator, or how do you call that D mono?
Yeah, usually I would call this, I guess, if you're precise, then you could call this the density matrix, and you can call this the matrix representation of the density matrix. That's how you sometimes say it. If you really want to differentiate this two quantities. And then, that kind of the one thing that we all know is that electron density, and electron density is just a density matrix if we use the same variable for the first and second coordinate. In other words, of course, it's just we take the square or the absolute square of the wave function and then integrate away all the electrons except the first one. So that's a description of the overall electron distribution. It's physically observable, and in some ways the electron density encodes all information there is, via the Hornberg-Kohn theorem. So there's some kind of more purists in kind of this wave function community that tell you, okay, you should only really ever look at the electron density because it's observable, and because the Hornberg-Kohn theorem tells you that that's the basis of density functional theory. It's really great. But then, then you actually look at the density. For example, this is the ground state for adenine. This is the N5 star state for adenine. This is the hyperstar, first hyperstar state, the second hyperstar state for adenine. So then kind of find, in principle, it's super amazing the selection density, but in practice, it doesn't really tell you anything. So then let's see where else we can go. So the next step that we can do is we can divide the electron density into different contributions. But the important thing is there's no unique way to do it. So there's no, there's no clear way of what part of the density corresponds to which atom. So one very famous way is a molecular population analysis. So basically you multiply the density matrix with the overlap matrix, and then you take the diagonal. So in a sense, you just take the diagonal density matrix element over every specific atom, and then you just have a specific bit of a correction for the non-optimality of the AOs that gives you the precise results, and it kind of then makes it a bit more complicated, but gives straightforward results. And then you can also do a Lefton population, which is take the square root of S and move it to the other side. There's many other options, there's beta charges from atoms and molecules, Hirschfeld charges, you can do the charges that come out of NBO or natural bond orbitals, you can fit to the electrostatic potential, and so on. So there's many different ways to define these charges. Here I'm just using the molecular charges, and just to give you an idea, if we take the molecular charges on the individual atoms, for the adenine molecule, and I'm just using the 4 nitrogen atoms here. And you see, okay, for the ground state, those are the same, then N9 is a bit different, because N9 has this hydrogen bonded to it, so you can kind of see some chemistry here. But then the point is, then we looked for the molecular charges in the different states, and you have, for example, for the n-pi star state, you see that something changes because the excitation comes from the orbital here, but it's also not great. So even molecular charges, some very basic thing that we compute for individual states. It gives you a bit of information, but it also doesn't give you the information you really care about normally. So then we can go one step ahead, rather than charges, we can try to compute pictures to get the natural orbitals. So now we have our density matrix here, or we set up matrix representation of the density matrix. This matrix, we can diagonalize it. And now the eigenvectors of the density matrix are called natural orbitals, and the eigenvalues are called the occupation numbers. And then we can either have, occupied closed shell orbitals with occupation number 2, the spatial orbitals. We could have unoccupied orbitals with occupation number 0, and we could have open shell orbitals or active orbitals with occupation number is between 0 and 2. So the example I had here, so this was, so we at some point we did, sharp surface of dynamics on this, I think, or even some quantum dynamics. So it was sodium iodide, so you have an NR sodium and an iodine atom. And here again, we want to know whether states ionic or biradical. This goes a bit back to kind of this famous one picture that we talked about. So when you when you separate them, the questions, do you have Na plus and I minus, or do you have Na radical and I radical? So then, here we look at the natural orbitals, and we see, okay, we have 3 W occupied natural orbitals. So this is kind of a closed shell. This is the iodine atom. Look at the 3 P orbitals, and the iodine atom are W occupied. So it's I minus, and then the 3 S orbital sodium is unoccupied. So then this has to be Na plus. For example, when we look at the the natural orbital, and we see this is Na plus and I minus. Just as one example how we read natural orbitals. For example, here we could also do molecular populations, of course. And and then, for example, the S0 state, then we see we have just 2 singly occupied orbitals. The 2 singly occupied orbitals are mixtures between the sodium S and the iodine orbital P. So then we can kind of realize that this is a biradical state where sodium and iodine and radical. And of course, if you pull the two atoms apart, then at some point they want to be neutral, because the kind of the Coulomb interaction is a very strong force. So if two things are far apart, then you don't want them charged. So it's kind of this 1/r expression that I showed also for the charge transfer. This Coulomb expression tends to win. So when we pull them apart, we want to be neutral. All right, so much about that. Kind of a density matrix is kind of logical starting point, but often it doesn't really solve our problem when we want to deal with excited states. So now when we want to compare two wave functions, psi 0 and psi I, we can kind of do the same thing we just did for the density matrix, only now we use the ground state wave function here, and we use the excited state wave function here. So we're plugging two different wave functions, and then we still remember the coordinate that we keep for this and this wave function. And now the coordinate that comes from the ground state is what we call hole. And the coordinate that comes from the excited state is what we call electron. So in a sense, this is kind of these two coordinates signify where the two wave functions differ. And then, and then kind of the difference ends up, can be interpreted as the electron hole path. And we can do the same thing as before. We can write this in second quantization, the matrix representation with creation and nivellation operators, and then again this connection from before. And here, so the important thing is that when we do this, we can identify those coordinates with the excitation hole and the excited electron, and then we get a two-body function that represents our excited state. So the physical meaning is that again we again have these operator expectation laws. Now we don't have expectation values, but we have the transition property. So if you want to know, for example, the transition moment or the oscillator strength, then you have to evaluate this expression, and you need the one-body transition density matrix. So that's also something that's readily available in quantum chemistry programs and has a clear physical interpretation. So, and while I'm here, I just want to cover one aspect that I think it's important in this context, that we can actually define a single excitation character, usually called as omega, as the Frobenius norm of this. So this we square all the elements and sum over all these squared elements. And now it turns out that these elements are the same elements as here. So for example, you can maybe the easiest way to see this is if this value is 0, then as a consequence that all of these transition density matrix has to be 0, and then any transition property of a one electron operator has to be 0. So, or more generally, we can kind of use omega as kind of the propensity of the two states to be coupled by one electron operator. And that's why, when we talk about singly or doubly excited states, and this is kind of one way how we can define singly and doubly excited states, where, if omega is 1, then, then you have lots of possibilities to couple those states with one electron operators. That's what we call a purely single excited state. Then let's say if omega is below 0.8, then we'd say we have significant involvement of higher excited states. And then if omega is 0, then then the two states cannot be coupled with any conceivable one electron operator. And there's some talk in the literature about how what is a doubly excited state? And in the MO picture, you look at a doubly excited state as okay, 2 electrons are promoted to 2 virtual MOs, but then obviously depends on what is your reference, what MOs do you use, what is correlation, what is excitation, and so on. And kind of the way that I think one could look at it is now that we say a doubly excited state, is a state that cannot be coupled to the ground state with any conceivable single electron operator. So then we kind of have a definition of doubly excited states that's all based on physical observables. And we don't need, we don't need to kind of invoke explicit MOs to talk about doubly excited states. So, okay, so that was kind of the detour. Then, and maybe something to say here is that kind of most of the transition density analysis techniques that we'll be talking about only work for single excited states. So if you have doubly excited states, then you can still use a different density matrix, but then then the transition density things don't work anymore because the transition density vanishes. We have the transition density as a, again, by taking the diagonal part of the transition density matrix. And here, basically, the physical meaning of the transition density is that the dipole moment of the transition density is the transition dipole moment, and that's how the molecule interacts with light. And so basically, if you want the transition dipole moment, you have to find all the blue parts and all the red parts, and then kind of draw an arrow from the center of the blue parts to the center of the red parts. So that's the physical meaning, but it's usually not easy to to actually understand what this means. So transition densities, I don't think transition densities are very good to represent excited states unless you have a very specific reason to do so. Because of all these different blobs that don't really tell you much. So then let's see how can we keep going. Remember we had the natural orbitals, which were the eigenvectors of the density matrix. Now we can kind of do the same kind of game with the transition density matrix and do a singular value decomposition of the transition density matrix. So the reason is the transition density matrix is not a symmetric matrix. That's why we're not doing getting the eigenvectors. We're doing a singular value decomposition. And then actually we get two different things. We get a matrix U that represents the whole, that represents where the excitation comes from, and a matrix V that tells us where the excitation goes to. So, that's, for example, is important for large basis sets or for more complicated excitation. As an example here, if you have some diffuse basis functions and we have the S4 state, then and we look at the excited state in canonical orbitals, it looks like this. We start out in this non-bonding orbital, and then we go into all these high-lying orbitals. And now the question is, what is the state character here? You see, as I told you in the first part, we have these kind of blobs that are far apart, and it's kind of a diffuse orbital. So then the question is, if we have to look at this, is this going to be a Rydberg state because of these diffuse orbitals? Or is it going to be an n-pi star state, or is it going to be a mixture? And in the canonical picture, you don't see it. So this is just kind of I don't know what code I used, maybe QChem, but it's just if I just read out the configurations, then that's what it tells me. And then the question is how do we interpret this? Yeah, so do we have, for example, Rydberg mixing? What do we have? So then. The thing to realize is that the individual orbitals don't have a physical meaning. So in a sense, what really matters is this this two-body function describing the electron hole pair, and then we just use these orbital pictures to describe our two-body electron hole functions. But the point is that kind of the orbitals that we use as a basis come from the ground state Hartree-Fokker DFT computation. And let's say these orbitals that come from the ground state computation aren't necessarily suited to tell us what the excited state looks like. So they don't have a physical meaning. They're just kind of intermediate quantities in Hartree-Fokker. Can be misleading, especially in Hartree-Fokker, the low energy virtual orbitals are diffuse because you have this continuum of a free electron at energy zero. So if you do Hartree-Fokker with an infinite basis set, then you have, you know, a continuum of just kind of unbound electrons at energy equals 0. And then, you know, if you have diffuse function, you just get part of this. And that's why you have all these low energy diffuse orbitals that kind of confuse your computation. So, yeah, but again, the thing that matters is the, you know, the transition density, the density matrix. And we'll replace through natural transition orbitals. And now what we find out is, you know, this was the same status before, and just it turns out that 97% of this transition is just this n pi star state. So we had all these orbitals, but that was a pure artifact of using Hartree-Fock orbitals. But in reality, the state is described with the 90% transitions in n pi stars. And I think that's important to realize that sometimes, you know, kind of the original computation gives you a completely wrong picture where, you know, wrong orbitals may be involved, where you kind of get some artificial multi-configurational character. So I would always suggest, you know, doing some rigorous transformation if you're interested in state character. And then you can think about the computation. So this pi orbital, if you just add up all those orbitals, if you perform this linear combination with all those orbitals, then you end up here. I guess you don't see it that well, but for example, this blue blob maybe cancels out against this red blob and so on. Or, I mean, you don't see it right well, but I mean, at the end of the day, you just add all these orbitals up, and then all the diffuse contributions cancel out, and you're left with a beautiful pi star orbital. So just kind of as a warning, if you just kind of look at Hartree-Fock orbitals, things can go completely wrong. So, and yeah, then sometimes the natural transition orbitals are a bit too much, so we can also, you know, compute the hole and electron density, so we can integrate out, you know, the electron current, the hole current. Actually, this will be squared. Yeah. And then, you know, then you have kind of one picture for the hole, one picture for the electrons, rather than several orbitals. And for example, you can compute the centroids of those, or you can compute how big are they. So for example, this is again our adenine computation. We compute the statistical moments here. So this is the size of the hole, and the hole size, and this is Z component, the size of the electron. And for example, what you can see now is the kind of the states where the electron size is much bigger, those are Rydberg states. So then basically then you have kind of again, you press a button and you know is the state a Rydberg state, because we just said, you know, the S4 state looked a bit like a Rydberg state because it had all these orbitals, but it's actually not. But then the S3 and the S5 still are Rydberg states. So again, you know, if you just look at canonical orbitals, things may be very confusing. But then if you use this kind of size of the electron distribution, you see, okay, it's much larger, it's a Rydberg state. And then you can also see kind of, you know, that this value is small because an n pi star. So pi orbital, you know, is taller, and n orbital is kind of squished together. If you look in the Z direction of our molecular line. So then you can, you know, in some cases you can kind of use these descriptors, how big is the hole, how big is the electron, to reduce the state characters with Rydberg, and also n pi star versus pi star if you're careful. Sometimes it works. Okay, then when we kind of talk through our toolbox, the next thing is the difference density matrix. Basically, we compute the density of the excited state density of the ground state and subtract those. Then we get difference densities. So the difference densities kind of tell us, you know, the red part is where the excitation comes from. The blue part is where the excitation goes to. And you know, you can kind of see in the n pi star state, the excitation comes from these bits, and it kind of goes through these bits. But you also see, I also don't like difference density matrices, because, you know, you see difference density matrices also all those kind of blobs that are hard to understand, and the problem is because then you also have some relaxation contributions. So you excite from here, but then, you know, the sigma system relaxes back to here. So with differences, you also don't really see very well what the excited state really is. So, so when in doubt, I also would use different density measures. There's all these different blobs and relaxation contribution. But what we can do, so it's all kind of the same story. But we can go to orbitals, so we compute the natural difference orbitals, which are now the eigenvectors of the difference density matrix. And then we can compute attachment detachment density, so that's something Martin Gordon has made popular, where we compute the weighted sum over these, or we compute the individual orbitals. So now these are ones are attachment detachment densities, and you see for the n pi star state, then you can kind of see, okay, you have the n orbitals here, and this is a pi orbital. Then you can see, okay, pi star state, you have a pi orbital here, pi star state, pi here, pi here. So attachment detachment densities are, reasonably well suited to show the character, but I still think natural transition orbitals are probably kind of the best way to actually see excitation character. Just kind of wanted to show you through, walk you through the different tools that people have developed and that are widely used in the scientific literature. Yeah.
This is the only graphical representation of the picture to see the sigma and pi bonds. This is actually, you can see on the basis of experimental tools.
This is an analysis of the wave function. So basically.
So I wanted to know, this is only like a graph, like a diagram, or?
Yeah, it's a diagram. So I think you can't, these things you can't. Yeah, so these are not physical observables. So I'll talk about that issue a bit later. But
if we are not able to see the actual sigma pi bond inside the molecule, then how we describe the Rydberg state or some other thing, and we just describe on the basis of particular result or some mathematical calculation or on the basis of matrices or quantum mechanics. But we do not have some stable interlink between experimental things and the particular.
Yeah, I mean, I think we can argue about these things for hours, but let's say, of course, you have kind of the experiment. You have things you can verify with experiment, whether it's the energy and the oscillator strength, and then kind of the idea is, you can verify, you can verify experimental observables, but then kind of the idea is with these things you can dig deeper. You can see things that experiment doesn't see. I mean, in a sense, I think that's the amazing thing about theory, that you can, let's say, visualize things that are in principle inaccessible by experiment. But of course, I mean, this is, this is a long discussion. But I would say, on the one hand, you want to make sure that you have some experimental observables to compare to. On the other hand, of course, the value of doing computation is to see things that you can't see in experiment, because if all you ever want to do is reproduce experiment, then it's better if you would just do the experiment rather than the computation. So we can talk about this a bit later if you want to. So then basically now the question was kind of we want to compare transition density and difference density. So we said, for example, now this is an n pi star. So it's a natural transition orbital study. Okay, go from this n orbital to pi star orbital, and then now so this is the transition density. This is the difference density, and you see kind of the difference density has the same initial contribution from the n orbital to the pi star orbital, but then you have these extra contributions, and it turns out that these extra contributions can be related to orbital relaxation. So basically, you have this pi orbital here. And then so we start moving density from the n orbital to this pi star orbital, but then this pi orbital kind of contracts and moves density back. And and you can also see that this sigma orbital also kind of contracts and moves density back here. So something that's kind of nice to see, and that you don't see, if you just look at the orbital transitions, is that whenever you excite an electron away from somewhere, then everything else, kind of the sigma system, the pi system relaxes back. And on the one hand, that's, I guess it's important to realize for the computational description that kind of more stuff happens, and you have to describe it with the computational method. And on the other hand, I think it's also kind of the reason why, why these difference densities are so complicated, because the difference densities don't only have primary excitation contributions, but you also have all these little relaxation effects. Okay. So then let me start with a case study. So this is how do we analyze push-pull systems? And I guess, the chemistry might not be that interesting at this point because we're more talking about techniques, but okay, it's just some colleagues of mine, we're making these molecules where you have like triphenylamine and the triazoles, and of course everyone's doing quick chemistry, which is also the reason Nobel Prize. You get different isomers, different oxidation states of this sulfur atom, and then at the end of the day they get the emission spectra for different structures, and the thing that they were really interested in is why is this one, the blue one here, the red one here, and the purple one here. And it turns out, that they're all kind of isomers. The question is just, do we attach it at this point or at this? Do we attach it at this point or at this point? And then is this in Z, an E or Z configuration? So that's kind of a typical question. Why are these? Why is? And maybe that also goes back to your question. So basically, you start with an experimental question, which is kind of why are the emission spectra so different between these? But then kind of you try to use theory to answer the question and give insight on the problem that you couldn't obtain with experiment. I mean, that's kind of the reason to do theory in the first place. So, we do some high-level computations, and at the end of the day, you can see that the excitation energies are reproduced if you try this long enough. So, I'll try to focus on the wave function analysis aspect. So try to do it fairly quick, but you see, kind of the ones where the excitation energy is very low, so the ones that are mostly redshift, they also have large dipole moments. So we can kind of understand, there's some solvent to chronic shift involved, the large dipole moments are stabilized by the solvent. And, so we can reproduce the trends. We get the shifts once we use the right method. But then the question is, why? So in a sense, if we just reproduce experiment, and then we haven't really provided any insight. So then we could try to do why, and then we can look at the frontier orbitals, look at the HOMO and the LUMO, but then we find out the first excited state is not only the HOMO-LUMO transition, but we also have the LUMO plus 2 involved. So, and that's kind of the thing that I was trying to preach is, frontier orbitals don't really tell the whole story, especially, here we're asking the question, does the excited state go from here to this part, or does the excited state stay on this right part? And and then with these frontier orbitals, you don't really know what's the case. So then what we do is we sum over all occupied and virtual orbitals. So it's like this whole in electron densities, which is again kind of the same thing as the natural transition orbitals, and then and then we plot the electron densities for different molecules and different solvents. And for example, what you can see is that if we use this solvent is not so polar, the electron density around here. If we use the more polar solvent, the electron density is pulled further to the accepted group. And then we can also compare the same thing as also for this molecule, and then for the molecule where we use the 1,5 substitution, the electron density is always on this acceptor group and never on triphenylamine like it's here. So what was the point of this? That we're going to use some rigorous techniques to visualize what's happening, and then we can also find this more subtle trends about how isomers and wave and solvent affects the wave function. And these trends, you wouldn't see if you just kind of look at canonical orbital. So, so we can kind of think about there's a bit of a larger dipole moment because this is linear rather than bent. And then here we can kind of identify a conjugation break. Okay, so then we have like this compact graphical representation with electron hole densities. Then, but we're still, still looking at lots of color. And then I just want to introduce one thing, and that's kind of, when people use theater, I think that's maybe one of the really the workhorses of theater, and that's this idea of this fragment-based excitation in the electron hole picture. So now we have a molecule that's separate into separate fragments. In our case, we think about this triphenylamine donor, then kind of this bridge group and the acceptor group. In some other cases, and then Quant has written a very nice paper about that, where you can have different DNA bases. And now we can think about, a local excitation means electron and hole are always on the same fragment. The charge transfer state means that the hole is in one fragment, the electron is over here. And then the delocalized exciton means that electron and hole are always on the same fragment together, but they kind of move through the system. And then we could also have charge resonance states where, the electron and hole are always, on opposing fragments. And then we can kind of turn this into a matrix representation where, so if electron and hole are always on one, then we have this element, then kind of, the hole is on two, electron one, and then you can try to turn these arrows into a matrix representation, so that, and then the local excitations are also on diagonal, and charge transfer excitation on the off diagonal. And this is what ends up being the charge transfer number, so it's often called omega AB, and this value then gives you the probability of the charge transfer from A to B, or the probability of a local excitation on A. And now this allows you to distribute the excitation over different fragments. So again, and here we're using in this case to have an automatic assignment of state character. And I think this actually a colleague in Vienna, Sebastian May, developed this kind of representation. And I'm kind of trying to push this because I think this turns out to just be an instructive way to talk about excited states. Often it's like, often you have this really long table that says, okay, energy, oscillator strength, and so it's like HOMO -3 to LUMO +1, 27%, HOMO -2 to LUMO 16%, and then you have this really long table, and at the end of the day, you don't know anything what's happening. And I think one way this Sebastian had to develop is this idea. So in the first part, you have the excitation energies. The black line gives you the excitation energy. And then we can use the shading for the oscillator strength. So the bright state is orange, the first state is bright. Then this state is also a bright state, and the third state is reasonably bright, and all the other states are dark. And down here, we see what what fragments are involved. So blue means that everything happens on triphenylamine. So for example, the S2 and the S3 states are mostly all on the triphenylamine donor. Then the S1 state, is 60% locally excited on triphenylamine, but then has some contributions going to triazole and some contributions going further out. And then, if we go up, then we see kind of the first, and then we see, for example, S7 and S8, they mostly happen on the triazole, so on this part here. So then, then you have one picture that tells you energy is also the strength and where the states are. So for multi-chromophoric systems, that's good to use. And in the tutorial, we'll talk about how to make a graph like this for a transition metal complex. I also put the research data, so if you want to try to reproduce this, I also put this. I can also show you. I'll do it depending on how far we get. And again, yeah, down here I'm just plotting the natural transition orbitals. So for example, this state, the blue state is only on triphenol M, and you see this with the natural transition orbitals. This state goes a bit further on this side, so that's why it's green. And for example, these states only happen here, and that's why it's orange. Okay. So then we see, for example, the brightest state is S1, it has some charge transfer character expand, this is TPA center. So again, you just kind of press a button, specify, you just have to specify the fragments, but anything else kind of happens behind the scenes, and then you get a plot like this, and you can, analyze the states, you can show trends and so on. Okay, then let me just go to the second case study, and that's about excitons. So, we're looking at oligothiophene. Oligothiophene is a prototypical conjugated polymer that's, studied like crazy by different people. We're using P50 can be 3 lips. So the only thing I should say here is that you need some kind of a range-separated functional if you want to get reasonable results in our conjugated polymers, because otherwise you have unbound excitons. But otherwise, we can get those pictures there, but then you can rapidly have to worry about it too much, at least from a qualitative point of view. Being quantitative, because then you want to have some negative T function. But then how do we analyze the states? And in the standard picture, again, you're running QChem or what it was, 2 more, and then you just see, okay, these are our canonical orbitals, and then you see all these states are linear combinations between different canonical orbitals. So the first one is homo-LUMO, and then homo -1, LUMO +1, and then, for example, we have the homo-LUMO +1, homo -1, LUMO, and and it just starts being a bit boring because you have all these delocalized pi orbitals. All these orbitals kind of look the same, all these orbitals kind of look the same. And then you just have a linear combination of many of them, and then you end up kind of with the problem, how do we talk about these states? And so should we say, okay, they're all kind of pi star states? But that's also what I meant in the first part, that there's so many that, you should never just say it's a pi star state, because, on the market there's so many different pi star states that just end up being a bit useless to say that. So, yeah, so all these locals orbitals, and then then you have these more specific things, where the S2 and the S3 state have basically the same orbitals involved, and the only difference is that we have a minus here. Then how can we understand what this minus sign means in a linear combination? So we need a different way to think about it. And I just showed you this. And, we look at the electron hole pair and we distribute the station between different fragments. So for this point, another thing that I want to stress now is that we're thinking about a 2-dimensional correlated picture. So we have an electron and a hole that kind of move through the system, and we really have to think about it as a 2-particle distribution, a correlated 2-particle distribution. And then how do we construct a 2-body exciton wavefunction? This is a bit copy-pasted together. So we just talked about this, of course. The solution is the transition density matrix, where this transition density matrix is interpreted as the exciton wave function, as a matrix representation of the exciton wave function, and then we can use this charge transfer number. So this same tool that we also used in last case study to see where it is, and now we're using what's called an electron hole correlation plot. So the way we do this is, we plot the hole coordinate here, the electron coordinate we plot along the y-axis, and then now all the different boxes are the different thiophene rings. So we have 1, 2, 3, 4, 5, 6 thiophene rings here. 1, 2, 3, 4, 5, 6 thiophene rings here. And then if the state is mostly on the main diagonal, then we have kind of this type of Frankel exciton state. So that's what we're talking. Main diagonal is Frankel exciton state, where the state is delocalized, but at any given point in time, electron and hole are always on the same fragment. And then if we have more or less this charge transfer action or charge resonance states, then we have off diagonal contribution. So we can see S1, S2, and S4 are mostly on the main diagonal. So these are locally excited states. And then S3 and S5 are the charge transfer excitons. So kind of the way we think about this is a little bit like a hydrogen atom in a box. So where this, and this would be the S orbital of the hydrogen atom, and this would be the P orbital of the hydrogen atom. So that's the normal plane along here. And then what's the difference between this one and this one? So this is the kind of the first excited particle in the box state. This is the second particle excited particle in the box state. And then this is the P orbital in the ground state of the particle in the box, and it's the P orbital in the first excited state of the particle in the box. So then we can kind of we use exactly the same computation that we had here, but rather than having all these kind of linear combinations that don't mean anything, we can kind of reinterpret this as as a hydrogen atom moving in a box. And now the question is, maybe you think it's still not very intuitive. What does it mean? Then one way to think about it is, we take our exciton wave function and we compute the conditional density. So what we do is we constrain the hole to one part of the system and take the square of our density matrix, and then we look at the resulting distribution for the electrons. So in practice, this is also just a few matrix operations. So we get the conditional density for the hole is localized on fragment A. So condition density for the electron under the assumption that the hole is localized to fragment A. So the overall electron distribution looks like this for the S1 state. And now if the hole is here on the side, and you see the electrons kind of pull toward the hole. If the hole is on the second one, it's still kind of on that side. And then if the hole is in the middle, and you see kind of the electron distribution kind of relaxes along with the hole. So the conditional electron density follows the hole. And then, we can kind of draw this. So this is the hole distribution. And then we can see the conditional density as the electron follows the holes, but when we move it through the system. So this is kind of how we can visualize this kind of static correlation between the electron and the hole in our exciton. Then, so as I mentioned this a little bit, so we can have these matrix plots, we can have the pictures of the conditional densities, but we can also evaluate operator expectation values with for the exciton wave function, and then especially this exciton size. So how far are the electron hole apart? That's useful in this context. Then we still get this kind of charge transfer here, but we don't need fragment definition or population analysis. So there's the S1 state, and for example, I see that the average separation between electron holes is 5.7 angstrom. So now, if you think about 5.7 angstrom, I guess maybe that's the separation between two of those rings. So, and this also kind of makes sense. I mean, maybe the separation between two boxes would be about 5 angstrom. So that's why I can mostly on the center here. And then we can also compute an electron hole correlation coefficient, just because I wanted to convince people this is electron correlation, where we just see, you can think about this as a two variable probability distribution, and then of course, if this is the probability distribution, there's some positive correlation coefficient. So for the S2 state, now the exercise is slightly smaller correlation is a bit higher, because because we have stronger correlation, as you have seen this nodal plane. So for example, when we look at this picture, and we see we start here, if the hole is on the left side, and the electron is always on the left side, and that's kind of represented by by this blob here. And then once the hole jumps to that side, the electron is always here. And then you can think about this p state. This p state is a much larger exciton size, so we follow the 5 angstrom, now at 9 angstrom. And we have a negative correlation coefficient, so the electron and the hole try to avoid each other in space. And you can kind of think about seeing this nodal plane. So now, if the hole is here, then the electron wants to be on the other side, and if we move the hole through the system, then you see how the electron kind of tries to avoid the hole as it moves along. Which is kind of how we can understand this correlated wavefunctions in larger molecules. Yeah, I think I'll skip this case study and go to the conclusions. So, the point that I wanted to make is, there's a wide variety of analysis methods, and the reason is because, there's also a wide variety of underlying physics, as I tried to show in the first talk. So you can think about what density matrix do you use normal density matrix, transition different density matrix, do you want to visualize pictures, do you want to have a population analysis, and quantitative descriptors. And I just, if you want to do this in practice, I just want to, as it's not always trivial, I just want to give you a bit of an idea, kind of some starting points if you have molecules that you want to talk about. So I think for well-behaved states in organic molecules, I think that natural transition orbitals are usually the thing that's easiest to interpret, that gives you all the information in the transition density matrix. So I would usually start with natural transition orbitals. They're easy to compute, easy to interpret. The only thing is that sometimes you have several pairs of natural transition orbitals, and then you have to there's important physics if you have several pairs of natural transition orbitals because it's related to correlation. But then you might want to have a bit of more complex representation. You could use this electron hole or attachment detachment density. For multi-chromophoric systems, we can use the charge transfer numbers. That's what we talked about in these push-pull systems and in these conjugated polymers, where we press a button and then you see kind of what local excited and charge transfer contributions are there. Is the exciton correlated? Use the exciton size as a quantitative descriptor. For Rydberg states, we use the size of the excess electron, sigma e, to see how it fuses the Rydberg orbital. That way, we can also see valence Rydberg maximum and stuff like that. And we can have the electron hole separation. That's also work for Rydberg states. The electron hole separation is also a nice thing. Then double excited state, as I said, we have this omega as a way to define double excited state character, independently of the method, just based on kind of this idea of operator expectation values. But for double excited state, the transition density matrix doesn't work. The natural transition also doesn't work because it vanishes. That's the whole point. Omega being 0, so then we need the difference density matrix if we want orbital pictures or analyzed charge. For multi-configurational states that are singly excited, and here, I'm talking about excitons. I'm talking also about ionic and covalent plus minus states like LA, LP, EP states. I didn't have time to talk about it. Then you can use what's called the NTO participation ratio to get the effective number of configurations. You can use electron hole correlation coefficients. We had that for the conjugate polymers to see how things correlate, and you can use the conditional densities to get some real space inside. And get the promotion of P for orbital relaxation, and that's about electrons rearranged. Okay, and then maybe one point you want enhanced flexibility. So for example, if a change in charge state, if you want to analyze what happens when you take away an electron, add an electron, or when you have independent computations. For example, sometimes you might have you might run like unrestricted quantum triplet states, and then you have the singlet ground state, and then you want to know what is the excitation from the singlet ground state to the triplet from a separate computation, and you can use this then you use a difference density matrix, and you can just analyze NOs. So that's the very last thing we'll talk about in the practical session. This script. I guess I think I'm all ready. Yeah, that's an individual state. Then we use the density matrix, of course, like in these natural orbitals or unpaired electrons. Okay. I also wanted to mention the software. So we'll be running stuff with Theodore later on. Theodore has interfaces to a wide range of quantum chemistry packages. You can get this from SourceForge. Then if you use QChem or OpenMorph or some limited cases also C4, then our tools are implemented, and you can use what's called libwfa. Then it's a bit easier to test things, and the functionality is a bit wider. But otherwise you have kind of this interface to those programs. The main scripts that you're going to be using in the afternoon is you also have to say Theodore first. So if Theodore theorem, you can generate the input. If you say Theodore analyze T, then you analyze transition densities, and then if you use analyze S and analyze NOs, then you can analyze state density matrices. So if you use starting with Theodore 3, you also have to say Theodore when you start the command, and Theodore 2, you call this analyze T.5, for example. So yeah, further reading. I mean, there's a book chapter that's still in print. I mean, if you ask me nicely, maybe I can give you a preview that contains all of the stuff that we've been talking about. And then there's a J-Chem Fisk paper that's more like an intro for practical computations, and there's this 20-page PCCP perspective that gives you some more of the underlying mathematics if you're interested in any of this. And then so I just prepared this as a final thought about all these topics. So this idea of Plato's cave, where most of us are like we're trapped in a cave and we don't ever see things how they really are, but we only sit here and look at the shadows of things. But then, then kind of what Plato says is, then you become a philosopher. You can leave the cave, go out and see how things really are. And I think I'm lucky here because only theorists in the room, I hope. But I think in a sense, you can also kind of see that's the kind of the separation between experiment and theory. You kind of have this experiment here, you have the spectrometer here, kind of try to and then it casts shadows on the wall, and then we look at those shadows, but some specific experiments tell specific aspects of specific molecules. And then kind of the point here is, obviously that's good to do that, but also, we can also become theorists, and see how things really are, and try to learn about molecules in ways that are not even in principle experimentally accessible. So and I think that's do not only try to reproduce the shadows on the wall. So I mean it's not that the only purpose of theory is to produce experimental results. Because if all we ever wanted to do was reproduce experimental results, then we'll do experiments. So I think as a theorist, I think you can realize that we can do things that we can't do with experiment, and things like what is an n-pi star state and a pi-pi star state. If you're rigorously only talking about physical observers, you could never say the word n-pi star state and pi-pi star state. But I think these are these are very useful concepts, and I think there's a lot of very useful concepts where where we are on this side that we should use and talk about, even if we can't see them in experiment directly. So of course we need the connection, but it's not about just reproducing experimental signatures look behind the screen. Then a bit of an advertisement. So we have a PhD studentship coming up about this. I guess all of you are probably already PhD students, otherwise you won't be here. But if you have anyone in the groups that you work with that's interested in this, let them know. I think it's not advertised yet, but will be hopefully soon. And then I just wanted to put up the names of kind of people that have supported me along the way in funding agencies. If I'm forgetting anything. Yeah, okay, thank you very much. Thank you very much, Felix, for this 2 hours nice talk. Do you have any questions before the coffee break? By the way, we also have here master students, so maybe they can also apply to the PhD position. Yeah. Okay, so just one quick curiosity. So, where are the orbitals? In the shadows or in the real world? And the orbitals are in the real world. Okay, so now we stop here. We go to the coffee break. So you can follow who is here from our group. So Hadi and Dario at the end of the room, because I have to take here some minutes. So you follow them, and then you go to the coffee break, and we are back. Let's delay 5 minutes. The next session at 12:15. Yeah.